NASA recently released images of the interstellar Comet 3I Atlas, and the world waited with anticipation. We expected clarity. We expected answers. We expected transparency from the agency that once put human beings on the moon. Instead, what we got was a press conference filled with reassuring words, blurry photographs, and a carefully constructed message that seemed designed more to calm public curiosity than to ignite it. And here's what makes this so troubling. Buried within those very images are 8 massive anomalies that defy simple explanation, statistical patterns that shouldn't exist, and mysteries so profound that any scientist worth their credentials should have been standing at that podium with barely contained excitement. Yet not a single one of these anomalies was mentioned. Not one. This isn't just disappointing. This is a fundamental betrayal of what science is supposed to be. Let me be clear about something from the beginning. When it comes to science, especially when an interstellar object enters our solar system, the first thing we need is humility. The second thing we need is honesty. You cannot pretend that you know all the answers when the evidence is still mysterious, when the data is still being analysed, when questions outnumber conclusions. That's not science. That's public relations. And what we witnessed in November 2025 was public relations dressed up in the language of scientific authority. We saw officials positioned in front of cameras. We heard carefully prepared statements. We watched as image after image was displayed on screens, each one accompanied by the same basic message. It's a comet. It's normal. There's nothing unusual here. Move along. But those of us who took the time to actually examine those images, who looked at the trajectory data, who consulted with radio astronomers and reviewed spectroscopic analyses, we saw something entirely different. We saw mysteries that demand investigation. We saw anomalies that challenge our assumptions. We saw exactly the kind of scientific puzzle that should make headlines, not get buried beneath bureaucratic messaging. Stay with me for the next several minutes, because what we're about to explore together isn't just about one comet passing through our cosmic neighbourhood. This is about how science communicates with the public that funds it. This is about transparency versus obfuscation. This is about whether we, as citizens who invest billions of dollars into space exploration, deserve to hear about the real mysteries our telescopes reveal, or whether we should be satisfied with sanitized summaries that protect us from the discomfort of not knowing. And make no mistake, there are 8 distinct anomalies connected to 3I Atlas that NASA's press conference completely avoided. 8 pieces of evidence that don't fit the simple narrative. 8 reasons to ask harder questions. By the end of this video, you'll understand each one of them. You'll see why they matter, and you'll recognize why their absence from that press conference represents something more troubling than mere oversight. Now, before we go any further, I need to ask something of you. If you believe that the public deserves scientific transparency, if you think that mysteries should be investigated rather than dismissed, if you agree that the agencies we fund owe us honesty, even when that honesty means admitting uncertainty, then hit that like button right now. And drop a comment telling me which of these 8 anomalies concerns you most, because I genuinely want to know what you think. I want to hear your perspective. This isn't about me lecturing to you. This is about all of us, together, demanding better from institutions that claim to represent scientific inquiry. Because what we're dealing with here isn't some fringe conspiracy theory. This isn't wild speculation disconnected from evidence. Every single anomaly I'm about to present comes from publicly available data, from peer-reviewed observations, from measurements taken by instruments like the Mars Reconnaissance Orbiter, the Very Large Telescope, and radio observatories around the world. The information exists. The mysteries are real. The question is why NASA chose to ignore them. Let me take you back to how this all unfolded. In the weeks leading up to November 2025, word began circulating that NASA had finally obtained detailed images of 3I Atlas using the Mars Reconnaissance Orbiter. This was significant because until that moment, every observation of this interstellar visitor had been limited by distance and resolution. We had spectroscopic data, we had brightness measurements, we had trajectory calculations. But we didn't have actual photographs that could reveal surface features, outgassing patterns, or structural details. So when NASA announced they would be holding a press conference to release these images, the anticipation within the astronomy community was palpable. Here, finally, was a chance to see this mysterious object up close. Here was an opportunity to examine it visually, to compare it with other comets, to search for clues about its origin and composition. Scientists around the world cleared their schedules. Journalists prepared questions. Space enthusiasts marked their calendars. Everyone expected this to be a moment of discovery. But then something interesting happened. The press conference got delayed. NASA cited the government shutdown as the reason, explaining that essential personnel weren't available, that clearances and approvals took longer than expected, that the release needed to be coordinated across multiple departments. Fair enough. Shutdowns cause disruptions. Nobody questioned that explanation initially, except for one small detail that many people missed. During this exact same period, while NASA was supposedly unable to release 3I Atlas images due to shutdown complications, the HiRISE camera team continued releasing other Mars images on irregular schedule. New photographs of Martian craters appeared online. Fresh observations of dust devils and seasonal changes were published. The Mars Reconnaissance Orbiter was clearly operational. Its imaging systems were clearly functioning. Its data pipeline was clearly active. So why were 3I Atlas images specifically held back? Why did those particular photographs require additional weeks of delay when similar images were flowing freely? This is the kind of detail that makes you pause, that makes you wonder if there might be more to the story than simple, bureaucratic slowness. When the press conference finally happened, the setup reinforced the sense of importance. NASA didn't just post images on a website with a brief technical note. They staged an event. They assembled officials. They created a formal presentation structure that signaled this was something the agency wanted to control, wanted to frame, wanted to manage carefully. And that's fine. Major discoveries deserve formal announcements. But here's what struck me as deeply wrong about the entire proceeding. The people who stood at that podium and spoke to the cameras weren't the scientists who had spent months analysing these images. They weren't the astronomers who had been tracking this object's unusual properties. They weren't the researchers who had noticed the anomalies I'm about to describe. Instead, we got administrative personnel, we got public affairs officers, we got individuals whose expertise lies in communication strategy, not in astrophysics or planetary science. These are competent professionals, no doubt. But they weren't the right people to be explaining what these images revealed, because the expertise required to truly interpret this data, to recognise what's unusual and what's expected, to answer technical questions with depth and nuance, that expertise was conspicuously absent from the stage. And the message they delivered matched their qualifications perfectly. It was smooth, it was confident, it was carefully designed to reassure rather than intrigue. We heard phrases like consistent with cometary behaviour, and within expected parameters, and no unusual features detected. The images themselves were displayed briefly, each one accompanied by simple captions that labelled the fuzzy bright spot as 3I Atlas, and noted the date and time of observation. Then the presentation moved on quickly, as if there was nothing more to discuss, as if these photographs were simply checking a box in the documentation process rather than revealing anything scientifically interesting. Questions from journalists were answered with the same bland reassurance. One reporter asked about the object's trajectory. Response: it's following a predictable path influenced by solar gravity and outgassing forces, nothing anomalous. Another asked about composition. Response: spectroscopic analysis suggests typical cometary materials, primarily water ice and dust, consistent, with expectations. A third asked about the object's size. Response: difficult to determine precisely from these images, but estimates are within reasonable ranges for comets. Every answer closed down curiosity rather than opening it up. Every response treated this interstellar visitor as mundane rather than extraordinary. But here's what NASA should have done, what any institution genuinely committed to scientific transparency would have done. They should have put actual working scientists at that podium. They should have displayed these images alongside detailed analysis, showing viewers exactly what the data reveals and what remains mysterious. They should have said something like this: we've obtained the first resolved images of an interstellar comet, and while some features match our expectations, there are several aspects that we find genuinely puzzling and worthy of deeper investigation. Let us walk you through what we see and what questions we're now pursuing. That would have been honest. That would have been exciting. That would have treated the public as intelligent adults capable of handling uncertainty. Instead, we got a performance designed to minimize interest, to package this extraordinary object as ordinary, to ensure that nobody left that press conference with uncomfortable questions lingering in their minds. And that choice, that deliberate decision to downplay rather than explore, to reassure rather than investigate, that's what brings us to the 8 anomalies that were completely ignored. Because the truth is, those images contain far more mystery than NASA acknowledged. The data they briefly displayed but didn't discuss reveals patterns that challenge simple explanations. The observations they mentioned in passing but didn't analyze in depth point toward phenomena that deserve serious scientific attention. And over the course of this video, I'm going to show you exactly what they chose not to show you, exactly what those blurry photographs actually reveal when you take the time to examine them carefully, when you compare them with theoretical predictions, when you place them in the context of everything else we know about interstellar objects and cometary behavior. You're going to see why the forward-facing plume that appears in multiple images represents something unprecedented in comet photography. You're going to understand why the timing of this image release raises questions about institutional transparency. You're going to learn why the ecliptic alignment of this object's trajectory is statistically shocking. You're going to discover why the detection of nickel without corresponding iron in spectroscopic data challenges our understanding of cometary chemistry. You're going to grasp why the sheer size of 3I Atlas, combined with it being only the 3rd confirmed interstellar object we've ever detected, suggests something profoundly unusual about either this object or our detection methods. You're going to explore why its trajectory brings it within degrees of the famous WOW signal's origin point in the sky, and why that coincidence deserves investigation rather than dismissal. And you're going to see why the object's non-gravitational acceleration patterns and perpendicular jet orientations don't match simple models of cometary outgassing. 8 anomalies, 8 mysteries, 8 reasons NASA should have been excited rather than dismissive. And we're going to examine every single one of them, not as conspiracy theories, not as wild speculation, but as legitimate scientific questions grounded in observational evidence. So let's begin with perhaps the most visually striking anomaly of all, something that's apparent in the very images NASA displayed but never discussed, and something that tells us this object might be behaving in ways we've never seen before. To understand why NASA's November 2025 press conference represents such a profound disappointment, you need to understand what the weeks leading up to it felt like for those of us who follow interstellar objects closely. This wasn't just another routine observation being added to the astronomical record. This was supposed to be a milestone, a genuine moment of revelation. Since the discovery of 3I Atlas earlier in the year, every observation had been limited by distance and atmospheric distortion. Ground-based telescopes could track its motion and gather spectroscopic data, but couldn't resolve its shape or surface features. Space telescopes like Hubble had scheduling constraints and couldn't dedicate extended observation time during the object's distant approach. So the announcement that the Mars Reconnaissance Orbiter had successfully imaged 3I Atlas during its relatively close pass by the Red Planet created enormous anticipation. Here, finally, was a platform that could capture this visitor in unprecedented detail. The MRO carries one of the most powerful cameras ever sent to another planet. Its high-rise instrument can resolve features as small as a meter across on the Martian surface from orbital altitude. Turned toward an interstellar comet, even at significant distance, it promised to deliver the clearest images humanity had ever obtained of an object born around another star. NASA understood this significance. That's why they didn't simply post the images on a technical archive website with minimal commentary, which is standard procedure for routine observations. Instead, they scheduled a formal press conference. They issued media advisories. They coordinated with news organizations. They built an entire event structure around the image release. This signaling matters because it tells you the agency recognized they had something important, something worthy of public attention, something that deserved more than a dry technical report. The space journalism community responded accordingly. Articles appeared previewing the upcoming release and speculating about what details might be visible. Social media buzzed with excitement as amateur astronomers and space enthusiasts shared countdown posts. Discussion forums filled with threads debating what features might be detectable, whether we'd see active outgassing, whether surface structure would be visible, whether the object might show any truly surprising characteristics. The anticipation built steadily over days, then weeks, creating exactly the kind of public engagement that space agencies supposedly want to encourage. People were paying attention. People were curious. People were ready to be amazed. Then came the delay. The The government shutdown that occurred during this period affected numerous federal operations, and NASA was among the agencies impacted. Essential missions continued, critical operations maintained their schedules, but many public-facing activities were postponed. Fair enough. These shutdowns create real complications, real disruptions to planned timelines. When NASA announced that the 3i Atlas press conference would need to be rescheduled due to shutdown-related delays, nobody questioned the explanation. Disappointment? Yes. Suspicion? No. These are institutional realities that sometimes interfere with scientific communication. The astronomy community simply adjusted expectations and waited for the new date to be announced. But during this waiting period, something peculiar became apparent to those who monitor Mars observation releases regularly. The HiRISE camera, the same instrument that had captured the 3i Atlas images, continued publishing new photographs of the Martian surface throughout the shutdown. New images appeared in the public archive showing freshly formed gullies, seasonal frost patterns, impact craters that had been targeted for study. The data pipeline was clearly operational. The team processing and releasing images was clearly working. The infrastructure for making Mars observations public was clearly functioning normally. So why were 3i Atlas images specifically being held back? If the delay was purely bureaucratic, purely about coordinating approvals and scheduling personnel for a press event, why not simply post the raw images online immediately and hold the formal press conference later? That's exactly what happens with most Mars observations. The images appear in the archive within days or weeks of being captured, and then if something particularly interesting is found, a separate announcement or press release follows afterward. But with 3i Atlas, the pattern was reversed. The images were captured in early October. They remained unreleased through late October, through early November, even as dozens of other Mars images were being published regularly. The special handling of these specific photographs suggested something beyond simple shutdown delays. It suggested a deliberate decision to control the timing and framing of their release, to ensure they were presented in a specific context with a specific message rather than allowing them to simply enter the public record and be analysed freely by the scientific community first. When the press conference finally took place in mid-November, the staging reinforced this impression of carefully managed communication. The setup wasn't casual. This wasn't a scientist giving an informal update from their office via video call. This was a formal event with multiple officials, with prepared statements, with coordinated graphics and slide presentations. The room was arranged like a major announcement. Cameras were positioned, lighting was professional. The atmosphere conveyed gravity and importance. And yet, despite all this ceremony, despite all this production value suggesting something significant was about to be revealed, the actual content delivered was remarkably thin. The officials who spoke weren't the researchers who had spent months analysing 3i Atlas. They weren't the astronomers who had been tracking its spectroscopic signatures. They weren't the orbital mechanics specialists who had been calculating its trajectory with increasing precision. They weren't the planetary scientists who might have compared these images with observations of other comets to identify what's similar and what's different. Instead, the presenters were administrative personnel, individuals whose expertise lies in public communication rather than in the technical details of interstellar object analysis. These are professionals who understand how to deliver messages clearly, how to avoid technical jargon, how to keep presentations accessible to general audiences. Those are valuable skills. But they're not the skills needed to actually explain what makes these observations scientifically interesting or puzzling. They're not the skills needed to recognize when data deviates from theoretical predictions. They're not the skills needed to articulate why certain features visible in these images deserve further investigation. So what we got was a presentation that described what the images showed at the most superficial level while avoiding any deeper analysis. We got captions and labels. We got confirmation that yes, this fuzzy bright spot in these photographs is indeed 3i Atlas, as observed from Mars orbit on these specific dates. We got reassuring language about the object behaving as expected, looking consistent with known cometary characteristics, presenting no unusual features that would require special attention. And the images themselves, while displayed prominently during the presentation, were shown briefly and without detailed examination. Each photograph appeared on screen for a few moments, accompanied by basic information: the date of observation, the camera settings used, the distance from Mars to the comet at the time of imaging. Then the presentation moved forward quickly, as if there was nothing more to say, as if these were merely documentary photographs confirming facts we already knew, rather than potentially revealing new information about an object we've never encountered before. Questions from journalists were fielded with the same careful blandness. When asked about the object's trajectory, the response emphasized predictability and normal gravitational influences. When asked about composition, the response cited spectroscopic analyses showing typical cometary materials without mentioning any anomalous detections. When asked about size estimates, the response acknowledged difficulty in making precise measurements from these images but suggested nothing unusual about the rough dimensions being inferred. Every answer functioned to close down inquiry rather than open it up, to reassure rather than intrigue, to present this interstellar visitor as mundane rather than mysterious. Compare this with what a genuinely transparent scientific press conference would have looked like. Imagine if NASA had put Dr. Somebody from the Mars Reconnaissance Orbiter Science team at that podium, someone who had actually examined these images in detail and compared them with theoretical models. Imagine if they had displayed each photograph slowly, zooming in on specific features, pointing out what's visible and what remains unclear. Imagine if they had said something like, "Here you can see an elongated brightness pattern extending in front of the object's nucleus, which is unexpected given the solar direction at the time of observation. We're not certain what causes this forward-facing glow, but it's something we want to investigate further because it doesn't match standard models of cometary dust and gas distribution." Imagine if they had acknowledged the statistical peculiarities in this object's trajectory, its chemical composition, its size relative to other detected interstellar objects, and then explained what observational campaigns were being planned to gather more data and test competing hypotheses. That would have been exciting. That would have been honest. That would have treated the public as intelligent partners in the scientific process, rather than as children who need to be protected from complexity and uncertainty. But that's not what we got. What we got was a performance, a carefully orchestrated presentation designed to generate minimal follow-up questions, minimal public curiosity, minimal demand for deeper investigation. And that choice, that deliberate decision to present these extraordinary observations as ordinary, to frame this unprecedented interstellar visitor as unremarkable, that's what makes this press conference such a profound failure of scientific communication. Because the evidence was right there in those images. The anomalies were visible to anyone who took the time to examine them carefully. The mysteries were apparent in the data that NASA possessed but chose not to highlight. And now, finally, we're going to look at what they avoided showing you, starting with the most visually striking anomaly that appears in multiple images but was never mentioned once during that entire presentation. Let me start by teaching you something basic about how comets work, because you need to understand normal behavior before you can recognize when something abnormal is happening. When a comet approaches the Sun, solar radiation heats its icy surface, causing frozen materials to sublimate directly from solid into gas without passing through a liquid phase. This outgassing creates the spectacular tails that make comets visible and beautiful, streams of gas and dust that can extend millions of kilometers into space. Now here's the crucial detail. These tails don't trail randomly behind the comet. They point away from the Sun. Always. This isn't a preference or a tendency. It's a physical law. Solar radiation pressure and the solar wind push gas and dust particles outward from the Sun. So regardless of which direction the comet is travelling, its tail extends in the anti-solar direction. If the comet is heading toward the Sun, its tail streams behind it. If the comet is moving away from the Sun, its tail actually extends in front of its direction of motion. If the comet is passing the Sun at an angle, its tail curves gracefully away from the solar direction. This pattern is so consistent, so fundamental to cometary physics, that it's one of the first things any astronomy student learns. Now, for most comet observations, the direction the comet is travelling and the direction away from the Sun are nearly aligned, especially when observing from Earth's perspective. When we photograph a comet approaching the inner solar system, we're usually seeing it move more or less directly toward the Sun, so the tail naturally appears to trail behind it like a banner. This makes the distinction between motion direction and solar direction difficult to separate in most images. We see a bright head and a tail extending backward, and both the physics and the geometry align perfectly. Our brains don't need to work hard to interpret what we're seeing, because the expected pattern matches what's visible. But here's why the Mars Reconnaissance Orbiter images of 3I Atlas are so significant. Due to the specific geometry of Mars's position, the comet's trajectory, and the Sun's location at the time these photographs were taken, for the first time we had an observation where the direction of the comet's motion and the direction away from the Sun were clearly separated. These aren't the same line in the sky. The comet was travelling along one vector, while the antisolar direction pointed elsewhere. This geometric separation gives us a unique opportunity to see which direction the brightness pattern actually extends, to distinguish between effects caused by the comet's motion and effects caused by solar influence. So what do these images show? Look carefully at the photographs NASA released, the ones displayed briefly during that press conference without commentary. The comet appears as a bright, slightly elongated smudge against the dark background of space, which is expected given the distances and camera resolution involved. But the elongation isn't random. The brightness pattern extends noticeably in one specific direction. And here's what makes this extraordinary. That extension points forward, along the direction the comet is travelling, not backward away from the Sun. Let me say that again because it's so important. The brightest, most prominent feature extending from this interstellar comet points ahead of its motion through space. There is a forward-facing plume, a concentration of brightness that precedes the nucleus rather than trailing behind it. This is not what cometary physics predicts. This is not what we see in typical observations. This is not behaviour that fits standard models of how dust and gas should distribute around an active comet. Now, let me be careful here. I'm not claiming this is impossible. I'm not saying the laws of physics are being violated. What I'm saying is that this pattern requires explanation because it doesn't follow the simple, expected mechanism. Under normal circumstances, material leaving the comet's surface gets pushed by solar radiation in the antisolar direction, creating that classic tail geometry. If we're seeing brightness extending in the direction of a motion instead, something else must be happening. Maybe there are gas jets erupting from the side of the nucleus facing forward, jets powerful enough to carry dust particles ahead of the comet before radiation pressure curves their paths back. Maybe the object is rotating in such a way that active vents are positioned to create this forward-throwing pattern. Maybe there's some unusual interaction between outgassing and the comet's motion through the interstellar medium, though at the speeds involved this seems unlikely to create visible effects. Maybe there are properties of the surface materials or the nuclear structure that we don't understand yet, properties that would explain why material is being expelled forward. These are all possibilities worth investigating. These are exactly the kind of questions that make observational astronomy exciting. You see something unexpected, you develop hypotheses, you design follow-up observations to test those hypotheses, you refine your understanding based on what the additional data reveals. This is textbook scientific method. This is how discovery happens. And this forward-facing plume should have been the headline finding of NASA's press conference. They should have displayed these images with arrows and annotations highlighting this feature. They should have explained why it's unusual and what potential explanations exist. They should have discussed what additional observations are needed to distinguish between competing hypotheses. They should have treated this as a genuine mystery worthy of public attention, because that's exactly what it is. Instead, they showed the images without comment, without analysis, without even acknowledging that anything unusual is visible. They presented these photographs as routine documentation, as confirmation of expected behaviour, as nothing more interesting than a checkbox being marked in their observational record. Why would they do this? Why would NASA avoid highlighting what might be the most interesting physical feature visible in these images? I can think of a few possible explanations, and none of them are particularly reassuring. One possibility is that the personnel running the press conference genuinely didn't recognise this feature as anomalous. Remember, these weren't the scientists who had analysed the images in detail. These were public affairs specialists who had been briefed on what to say and what points to emphasise. Maybe the briefing they received from the actual science team didn't flag this forward-facing pattern as significant. Maybe the analysis hadn't been completed by the time the press conference was scheduled. Maybe there's internal disagreement about whether this feature is truly unusual or just an artifact of the imaging process. These are all plausible, innocent explanations rooted in institutional complexity and communication gaps, rather than in any deliberate attempt to mislead. But there's another possibility, one that's harder to dismiss given the overall pattern of how this entire image release was handled. Maybe NASA recognised exactly how interesting this feature is, and made a conscious decision not to draw attention to it, because unexplained anomalies create public questions that can't be answered with reassuring soundbites. Maybe the institutional priority was to present this interstellar object as thoroughly understood and completely normal, rather than to acknowledge genuine mysteries that would invite speculation and demand follow-up investigation. Maybe the concern was that highlighting unusual features would generate media coverage framing this as a mystery object, potentially using sensationalistic language, potentially drawing comparisons to previous interstellar visitors that sparked controversial hypotheses, potentially creating public expectations for definitive answers that science isn't ready to provide. So instead of engaging honestly with the uncertainty, instead of treating the public as capable of handling complexity, the decision was made to simply avoid mentioning anything that might complicate the preferred narrative. I respect NASA enormously. The agency has accomplished extraordinary things. The scientists working within its various divisions are among the most talented and dedicated researchers in the world. But institutions, even great institutions, sometimes make choices that prioritize public relations over scientific transparency. They make choices designed to avoid controversy rather than embrace discovery. They make choices that underestimate the public's capacity for curiosity and overestimate their need for reassurance. And when those choices result in genuine, scientific anomalies being buried beneath bland press statements, when they result in imagery containing unprecedented features being displayed without commentary, when they result in opportunities for public excitement about cosmic mysteries being deliberately suppressed, those choices deserve criticism. Because this forward-facing plume visible in the MRO images represents exactly the kind of puzzle that should capture imagination, that should drive scientific inquiry, that should remind all of us why we explore space in the first place. The fact that it went completely unmentioned in NASA's formal presentation of these images tells us something troubling about how the agency currently approaches communication about unexpected findings. And this is only the first of 8 anomalies that were ignored, each one building on the last to create a cumulative case that something very unusual is happening with this interstellar visitor, and that the public deserves to know about it. Sometimes the anomaly isn't in the data itself. Sometimes the anomaly is in how the data is handled, how information is controlled, how transparency is selectively applied depending on what the information reveals. And that brings us to the second major issue with NASA's release of these 3i Atlas images: the suspicious timing and the inconsistent approach to making Mars observations public during the exact period when these particular photographs were being withheld. Let me walk you through the timeline because the sequence of events matters here. The Mars Reconnaissance Orbiter successfully imaged 3i Atlas during early October 2025 when the comet's trajectory brought it relatively close to Mars's position in space. This wasn't a difficult observation to execute. The MRO has been operational for years. Its high-rise camera is extraordinarily reliable, and targeting a bright moving object against the stellar background is well within its capabilities. The images were captured, transmitted back to Earth, and received by NASA's Deep Space Network without any reported technical issues. By mid-October, those images existed in NASA's data systems, ready to be processed and released. Now here's where things get interesting. NASA didn't release those images in mid-October. They didn't release them in late October either. Throughout this entire period, the agency remained silent about what those photographs showed, offering no updates, no preliminary reports, no hints about what had been observed. This wouldn't be particularly unusual except for one crucial fact. During this exact same time frame, the HiRISE team was actively releasing dozens of other Mars images on their regular schedule. New photographs of Martian surface features were appearing in the public archive consistently throughout October and into November. Images showing sand dunes, impact craters, polar ice deposits, gullies, and seasonal changes were being processed and posted publicly without delay. The infrastructure was working, the personnel were working. The standard pipeline for taking raw MRO observations, processing them into viewable formats, and making them available to scientists and the public was functioning normally. Yet 3i Atlas images specifically were being held back. When the government shutdown occurred, NASA cited this as the reason for the delay in releasing the Comet images and holding the scheduled press conference. And yes, shutdowns create complications. Essential personnel continue critical operations, but many routine activities get postponed. Public-facing events get rescheduled. Coordination becomes more difficult when portions of the workforce are furloughed, I understand all of this, but the explanation doesn't hold up under scrutiny because the HiRISE team didn't stop releasing Mars surface images during the shutdown. They continued publishing new observations throughout the entire period. If shutdown complications prevented the release of 3I Atlas images, why didn't those same complications prevent the release of images showing Martian craters and dunes? The data pipeline is the same, the processing systems are the same, the personnel involved are largely the same. So why were images of an interstellar comet treated differently than images of Mars surface features? The obvious answer is that 3I Atlas images required higher-level approval before public release. Someone in NASA's administrative structure decided these particular observations needed special handling, needed careful review, needed strategic framing before they could be shared with the scientific community and the public. That decision itself raises questions. Why would images of a comet require more bureaucratic oversight than images of a planet? What is it about photographing an interstellar visitor that triggers additional layers of approval and delay? The most generous interpretation is that NASA recognized the high public interest in this object and wanted to ensure the images were released with proper context and explanation rather than being posted raw into an archive where they might be misinterpreted. That's a reasonable concern. But the result of this concern was weeks of unnecessary delay, followed by a press conference that provided minimal context and even less substantive explanation. So the claim justification for special handling doesn't actually align with what the special handling delivered. The less generous interpretation is that someone reviewing these images recognized they contained anomalous features that didn't fit simple explanations, features that might generate uncomfortable questions if released without careful messaging to shape public perception. So the decision was made to hold the images while that messaging was crafted, to ensure that when they were finally shown to the world, they would be presented in a framework emphasizing normalcy and reassurance, rather than mystery and investigation. The press conference itself supports this interpretation. Everything about how that event was structured, from who presented to what was said to which questions were avoided, suggests a primary goal of managing public reaction, rather than transparently sharing scientific findings. This isn't how science is supposed to work. This isn't how publicly funded research is supposed to be communicated. When data is gathered using instruments and missions paid for by taxpayers, that data belongs to the public. It should be released as quickly as practical considerations allow, with transparency about what's known and what remains uncertain. Instead, what we got with 3I Atlas was selective transparency. Some data was shared freely and quickly, other data was held back, controlled, released only within carefully managed parameters, and the pattern of which data was treated, which way suggests the determining factor wasn't technical or scientific, but rather was about managing narrative and controlling public perception. That's a problem. That's a fundamental problem for an institution that depends on public trust and public funding. Because when people sense that information is being withheld or manipulated, when they notice inconsistencies in how different types of observations are handled, when they see delays that don't have convincing explanations, trust begins to erode. Not just trust in NASA specifically, but trust in scientific institutions more broadly. And that erosion of trust has consequences far beyond this one object. Consequences for public support of space exploration. Consequences for how scientific findings are received and understood. Consequences for whether future discoveries will be accepted or doubted based on suspicions about institutional motives. Let me be clear about what I'm not saying. I'm not suggesting there's some grand conspiracy to hide the truth about interstellar objects. I'm not claiming NASA knows this comet is artificial and is covering it up. I'm not buying into paranoid narratives about secret knowledge being concealed from the public. What I'm saying is much simpler and in some ways more troubling. I'm saying that NASA's handling of these images reveals an institutional culture that values message control over transparency, that prioritizes avoiding difficult questions over honestly acknowledging uncertainty, that treats the public as an audience to be managed rather than as stakeholders, deserving full access to the information their dollars paid to gather. And I'm saying that this approach is corrosive to science, corrosive to trust, and completely unnecessary. Because the public can handle complexity. The public can handle mystery. The public can handle hearing that scientists observe something unexpected and aren't yet sure how to explain it. What the public struggles to handle, what creates suspicion and conspiracy theories and loss of institutional credibility, is exactly the kind of carefully managed, Non-transparency that NASA demonstrated in this case. So this timing anomaly, this inconsistency in how different MRO images were handled during the same period, this bureaucratic delay followed by a substance-free press conference, this represents the second major failure in how NASA approached 3I Atlas. The first was avoiding discussion of the forward-facing plume visible in the images themselves. The second was manipulating the timing and framing of when and how those images were released. Both failures point toward an institution more concerned with controlling narrative than with sharing discovery. And both failures make the subsequent anomalies even more significant, because they establish a pattern of avoidance that extends beyond any single physical observation to encompass NASA's entire approach to this interstellar visitor. Now let's move from questions about institutional behaviour to questions about the object itself, starting with one of the most statistically improbable aspects of 3I Atlas, where it came from and how it arrived here. To understand why the trajectory of 3I Atlas represents such a striking anomaly, you need to understand something about the geometry of our solar system and what we should expect from objects arriving from interstellar space. Our solar system is essentially flat. All the planets orbit the Sun in roughly the same plane, a disc-shaped region called the ecliptic. This isn't coincidental, it's a natural consequence of how planetary systems form from rotating clouds of gas and dust that collapse and flatten into a disk before planets coalesce within it. So when you look at the solar system from the side, you see all the major planets orbiting within a relatively thin band, with some minor variations in inclination but nothing dramatic. Earth, Mars, Jupiter, Saturn, all of them circle the Sun in nearly the same geometric plane. This ecliptic defines the fundamental coordinate system we use to describe positions and motions in space. It's the reference plane from which we measure inclinations, the baseline against which we compare trajectories. Now, when we think about interstellar objects that formed around other stars and travelled through the galaxy, before encountering our Sun, we have no reason to expect them to arrive along the ecliptic plane. They're coming from random directions in three-dimensional space. The galaxy is vast. Stars are scattered throughout it in all directions. An object ejected from another planetary system could be travelling on any imaginable trajectory, at any angle from any region of the sky. Statistically, interstellar visitors should arrive from a roughly uniform distribution across the celestial sphere. Some might come from above the ecliptic plane, some from below, some nearly aligned with it. But the specific alignment with the ecliptic should be no more likely than any other angular orientation. It's like imagining rain falling on a tilted roof. The raindrops don't preferentially hit along the slope of the roof. They fall vertically regardless of the roof's orientation. Similarly, interstellar objects should arrive from all angles regardless of the solar system's flat geometry. So here's the shocking thing about 3I Atlas. Its trajectory brought it into the solar system almost perfectly aligned with the ecliptic plane. Not wildly inclined, not approaching from high above or far below the plane of the planets, but rather travelling along a path that lies nearly within that same thin disk that defines our planetary orbits. When you calculate the object's orbital inclination, the angle between its trajectory and the ecliptic plane, you find it's remarkably small. This isn't a matter of interpretation or subjective assessment. It's a quantifiable geometric fact that can be measured precisely from the object's observed motion. And that measurement reveals an alignment that shouldn't happen by random chance with high probability. Let me put this in concrete terms. If interstellar objects arrive from truly random directions, the probability of any single object arriving with an ecliptic inclination, this low is roughly 1 in several hundred. The exact number depends on how you define the boundaries of what counts as aligned versus inclined, but the general magnitude is clear. This is statistically unusual. This is not something you expect to see when you detect only a handful of interstellar objects total. Think about what this means. We have now detected 3 confirmed interstellar objects, Oumuamua in 2017, 2I Borisov in 2019, and 3I Atlas in 2025. That's our entire sample, 3 objects. And one of them, the most recent one, arrives along a trajectory that aligns with our solar system's fundamental plane in a way that should be rare. If we had detected hundreds or thousands of interstellar visitors, finding 1 or 2 with unusual alignments wouldn't raise any eyebrows. Statistical distributions always include outliers, but we haven't detected hundreds. We haven't even detected a dozen. We've detected 3. and the third one shows this peculiar geometric property that statistically should occur in only a small fraction of cases. That's the anomaly. That's the puzzle that demands explanation. Why does 3i Atlas arrive along the ecliptic when random chance suggests it most likely should not? Now let's consider possible explanations, because my goal here isn't just to list mysteries, but to think through what they might mean. One possibility is pure luck. Maybe we simply happen to detect an object that, by coincidence, arrived along an unusual trajectory. With a sample size of 3, we don't have enough data to draw strong conclusions about the underlying population distribution. Maybe the next dozen interstellar objects we detect will all arrive from highly inclined trajectories, and 3i Atlas will turn out to be the rare exception, the one in several hundred case that happened to occur early in our detection history. This explanation is logically possible, unlikely things sometimes happen. The fact that something has low probability doesn't mean it can't occur. If you flip a coin 10 times and get 10 heads in a row, that's unlikely but not impossible. Similarly, detecting an ecliptic-aligned object among our first few interstellar discoveries is unlikely but not impossible, so we can't rule out simple chance as the explanation. But there are other possibilities that deserve consideration. Possibilities that might actually be more scientifically interesting, because they would teach us something new about how interstellar objects move through the galaxy, or how our detection methods work. One alternative explanation involves gravitational focusing. The galaxy has structure, there are density gradients, spiral arms, regions where stars are more concentrated. The Sun is moving through this galactic environment, orbiting the galactic center in a specific direction. It's possible that the Sun's motion through the galaxy creates a preferential direction from which interstellar objects are more likely to encounter our solar system, and that direction might be correlated with the ecliptic orientation for complex dynamical reasons related to how the solar system formed and how its angular momentum vector relates to the galactic coordinate system. This is speculative, and I'm not aware of detailed modelling that would support or refute this idea, but it's the kind of hypothesis that could potentially explain why the object's arrival direction isn't truly random. Another possibility relates to detection bias. Maybe we're better at detecting interstellar objects that arrive along the ecliptic plane for observational reasons. Most asteroid and comet survey programs scan the sky systematically, but they tend to focus more attention on regions near the ecliptic where solar system objects are concentrated. If an interstellar visitor approaches along a highly inclined trajectory, passing through regions of the sky that are surveyed less frequently or with less sensitivity, it might be more likely to go undetected. Conversely, an object arriving near the ecliptic would pass through heavily monitored regions where our chances of spotting it are maximized. This could create a selection effect where the interstellar objects we discover aren't representative of the true distribution of arrival angles, but rather a bias toward ecliptic-aligned trajectories simply because those are easier to detect. This is a testable hypothesis. If it's correct, then as our survey capabilities improve and expand coverage to all regions of the sky, with equal sensitivity, we should start detecting more highly inclined interstellar objects, and the apparent preference for ecliptic alignment should disappear. There's also a more speculative possibility that I hesitate to mention, but that deserves at least acknowledgement given how unusual this alignment is. If an object's trajectory is influenced by something other than natural gravitational dynamics, if for example it were receiving course corrections or had been deliberately aimed toward our solar system, alignment with the ecliptic might be exactly what you'd expect because that's where the interesting targets are. All the planets orbit in that plane. If something wanted to study our planetary system, arriving along the ecliptic would be the logical approach geometry. Now, I want to be very careful here. I am not claiming that 3i Atlas is under intelligent control. I am not arguing that this alignment proves artificial origin. What I'm saying is that when you find statistical anomalies in observational data, you consider all possible explanations, and one category of possible explanations involves non-natural influences on trajectory. This doesn't mean that explanation is correct or even likely. It simply means it's on the table along with other possibilities, to be evaluated based on evidence rather than dismissed out of hand because it seems uncomfortable or unlikely. And here's the crucial point that brings us back to NASA's press conference. Regardless of which explanation is correct, the ecliptic alignment of 3i Atlas is a feature that deserves discussion. It's a quantifiable observation that raises legitimate scientific questions. It's exactly the kind of detail that makes an object interesting, that prompts deeper investigation, that should be highlighted when presenting findings to the public. Yet NASA's presentation mentioned nothing about trajectory alignment, nothing about the statistical improbability of this arrival geometry, nothing about what this might tell us about interstellar object populations, or detection biases, or galactic dynamics. The briefing treated 3I Atlas as if its trajectory were utterly mundane, as if there were no geometric features worthy of comment, as if the path it travelled to reach our solar system held no information value whatsoever. That's not just an oversight. That's a pattern of avoidance that's becoming impossible to ignore. First, the forward-facing plume wasn't mentioned. Then the timing irregularities weren't explained. Now the trajectory alignment isn't discussed. These are three separate anomalies, three distinct ways in which 3I Atlas deviates from simple expectations, and all three were completely absent from NASA's official presentation of the data. This pattern tells us something important. It tells us that the bland reassurances we heard during that press conference, the claims that everything looks normal and expected and unremarkable, those claims are not supported by the actual evidence. The evidence reveals an object with unusual visible features, unusual timing in its data release, and unusual trajectory geometry. These mysteries don't automatically mean anything sinister or extraordinary is happening. They simply mean we don't fully understand this object yet, that there are questions requiring investigation, that the observations don't all fit neatly into simple models, and that's okay. Science is supposed to be comfortable with uncertainty. Science is supposed to pursue mysteries rather than hiding them. But that comfort with uncertainty, that enthusiasm for investigation, that's not what NASA demonstrated in how they handled these observations. Instead, they demonstrated exactly the opposite, a clear preference for presenting certainty even when the data supports questions, for projecting understanding even when mysteries remain, for reassuring the public rather than inviting them to share in the excitement of genuine discovery. And as we continue examining the remaining anomalies, this pattern will only become more clear, more troubling, and more difficult to excuse as simple communication failures rather than deliberate choices about what the public deserves to know. Now we move from geometric anomalies to chemical ones, from questions about where this object came from to questions about what it's made of, and this is where things become truly puzzling, in ways that challenge our understanding of how comets form and what materials they should contain. To appreciate why the spectroscopic observations of 3I Atlas represent such a significant mystery, you need to understand some basic principles about elemental composition and how different elements are created in the universe. Every atom of every element was forged in specific nuclear processes. Hydrogen and helium formed in the Big Bang. Everything heavier, all the carbon and oxygen and iron and nickel that make up planets and people and comets, was created later inside stars through nuclear fusion, or during the violent explosions that mark the deaths of massive stars. These processes don't create elements randomly. They follow specific pathways determined by nuclear physics, pathways that produce certain combinations of elements together in predictable ratios. Iron and nickel are particularly interesting in this regard because they're closely linked in how they form. Both are products of stellar nucleosynthesis, created during the late stages of massive star evolution and dispersed into space when those stars explode as supernovae. The nuclear reactions that produce iron naturally produce nickel as well, and the resulting material, the dust and gas that gets ejected into interstellar space and eventually incorporates into new solar systems, contains iron and nickel in relatively consistent proportions. This isn't a loose correlation. This is a fundamental signature of how stellar nucleosynthesis works. When you analyze the composition of asteroids, meteorites, comets, or planetary materials, you consistently find that wherever iron is present, nickel is present too in predictable amounts. The exact ratio varies depending on specific formation conditions, but the association between these two elements is robust and well established. They occur together because they formed together in the same stellar environments through related nuclear processes. So when astronomers point spectroscopes at comets and analyze the light coming from gases released by their surfaces, they look for spectral lines corresponding to different elements. Each element produces a unique pattern of lines, a fingerprint that allows identification and quantification even from enormous distances. iron produces certain characteristic spectral features when it's vaporized and energized by sunlight. Nickel produces others, and in typical observations of typical comets, when you detect iron lines in the spectrum, you also detect nickel lines, just as theory predicts. The presence of one confirms the presence of the other. This isn't just expected, it's essentially universal in every cometary analysis that's been conducted with sufficient sensitivity to detect these elements. Until 3I Atlas. During spectroscopic observations conducted by the Very Large Telescope in the latter part of 2025, something unprecedented appeared in the data. Astronomers detected clear spectral signatures of nickel in the light coming from 3I Atlas. The characteristic emission lines were unmistakable, strong enough to measure accurately, unambiguous in their identification. This object contains nickel in its composition, and that nickel is being released as gas through outgassing or sublimation processes, as the comet heats up in its approach toward the Sun. But here's the shocking part. The corresponding iron signatures that should accompany those nickel detections were either absent or present only at surprisingly low levels. The spectrum showed nickel without the expected proportional amount of iron. This is chemistry that doesn't make sense based on what we know about how these elements form and how they should be associated in natural materials. It's like finding rust without iron, or finding smoke without fire. The presence of one without the expected presence of the other violates the patterns we've observed consistently in every other context. Now, before we get carried away with speculation, let me acknowledge the observational complexities. Detecting elemental abundances in comets is difficult. Spectroscopy at these distances requires extremely sensitive instruments and careful analysis. There are potential confounding factors. Maybe iron is present but in a form that doesn't produce strong spectral lines under the specific conditions of 3I Atlas's outgassing. Maybe the surface temperature distribution creates unusual vaporization patterns where nickel volatilizes preferentially, while iron remains locked in refractory particles. Maybe there are geometrical effects related to where the outgassing is occurring and which portions of the coma we're observing spectroscopically that create apparent abundance anomalies that don't reflect the object's true bulk composition. These are all legitimate possibilities that need to be considered and tested through additional observations and modelling. But even granting all these caveats, even acknowledging measurement uncertainties and interpretational complications, the fact remains that what we've detected is unusual. No previous comet has shown nickel detections without corresponding iron at expected levels. This is, as far as existing astronomical literature indicates, a unique observation. And unique observations demand explanation, because they're telling us something unexpected is happening, something that doesn't fit our current models. So let's think through what that explanation might be. One natural possibility involves extreme fractionation during the object's formation. Maybe 3I Atlas formed in an environment with very unusual conditions that somehow separated iron and nickel in ways that don't normally occur, perhaps extreme temperatures, or unusual chemical reactions in the protoplanetary disk where it originated, or some other formation pathway we haven't fully considered. This would require quite specific circumstances different from those that produced every other comet we've studied, but it's not physically impossible. Another possibility relates to the object's history after formation. Maybe it experienced some event during its journey through interstellar space that altered its surface composition, preferentially removing iron or adding nickel. Perhaps a close pass by another star exposed it to radiation that changed surface chemistry. Perhaps impacts from interstellar dust grains over millions of years eroded outer layers in ways that affected elemental ratios. These scenarios are speculative and would require detailed modelling to evaluate their plausibility, but they represent attempts to explain the observation within natural frameworks. Then there's a more intriguing possibility that deserves mention, even though it ventures into territory that makes many scientists uncomfortable. Nickel alloys have properties that make them useful in aerospace engineering and high-performance materials applications. Certain nickel-based alloys are used in spacecraft construction specifically because of their strength, heat resistance, and other desirable characteristics. The presence of nickel without proportional iron is actually a signature you might expect to find in refined metallurgical products, rather than in natural unprocessed materials, because refining processes can separate and concentrate elements in ways that nature doesn't normally accomplish. Now, I want to be extremely clear about what I am and am not saying here. I am not claiming that 3i Atlas is made of engineered materials. I am not arguing that these spectroscopic observations prove artificial origin. What I'm doing is noting that the detected chemical pattern resembles something we associate more with processed materials than with pristine natural compositions, and that this resemblance is worthy of acknowledgement and investigation. The scientific method requires considering all possible explanations for anomalous data, including explanations that might seem unlikely or uncomfortable, and then evaluating those explanations based on evidence rather than preconception. If the nickel without iron signature can be explained by unusual but natural formation conditions or observational effects, then that's what the explanation is, and we'll learn something interesting about cometary chemistry. If it can't be explained that way, if further observations confirm that this composition truly is unprecedented in natural objects, then we need to be willing to follow the evidence wherever it leads, even toward conclusions that challenge our assumptions. And here's where I become frustrated with how NASA handled this. The spectroscopic data showing nickel detection exists. It was gathered by one of the world's premier telescopes. It was analysed by competent astronomers who understand elemental identification. The observations are in the scientific record, available to anyone who knows where to look and how to interpret spectroscopic measurements. This isn't hidden information. This isn't classified or secret. It's simply public scientific data that didn't get mentioned in the press conference. Why not? Why would NASA's presentation of 3i Atlas observations omit any reference to the most chemically anomalous aspect of what's been detected? The most generous interpretation is that the spectroscopic results hadn't been fully peer-reviewed or independently confirmed by the time the press conference was held, so the decision was made to stick with imaging results and not discuss chemical composition. That's defensible as a conservative approach to science communication. You don't want to highlight preliminary findings that might not survive further scrutiny. But the pattern we're seeing suggests something less innocent. We've now identified 4 separate aspects of 3i Atlas that are unusual or anomalous: the forward-facing plume, the timing irregularities, the ecliptic alignment, and the nickel detection. 4 distinct observations that all point toward this object being more interesting, more mysterious, more worthy of investigation than NASA's bland presentation suggested. And all 4 were omitted from or downplayed in the official briefing. That's not random. That's not accidental. That's a pattern of deliberate selection, a choice to present only the information that supports a nothing to see here narrative, while avoiding anything that might complicate that narrative or invite difficult questions. This approach might make sense from a public relations standpoint if your goal is to minimize controversy and avoid speculation. But it's terrible science communication. It's a betrayal of the principles of transparency and open inquiry that are supposed to define how publicly funded research is conducted and shared. The public funds these telescopes. The public pays for these observations. The public has a right to know when those observations reveal something unexpected, even if scientists aren't yet sure how to explain it. Saying, "We've detected nickel in unusual abundances, and we're working to understand what that means," is honest and appropriate. Saying nothing at all about it while presenting a carefully curated selection of uncontroversial findings is dishonest and inappropriate, regardless of the institutional motivations behind that choice. Because here's what happens when this pattern continues, when anomaly after anomaly goes unacknowledged by official channels while being visible to anyone who examines the data independently. People start asking why. People start doubting institutional credibility. People start wondering what else isn't being mentioned, what other observations are being selectively filtered to manage public perception, rather than shared openly to invite collective inquiry. The erosion of trust that results from this approach ends up creating exactly the environment of suspicion and speculation that the approach was supposedly designed to prevent. If NASA had addressed the nickel detection honestly, had said something like, "We've observed unusual spectroscopic signatures that we're still working to interpret, and we're planning additional observations to confirm these findings and understand their implications," the response would have been fascination and support, not panic or wild conspiracy theories. The scientific community would have recognized this as responsible acknowledgement of uncertainty. The public would have appreciated the honesty. The conversation would have remained grounded in evidence and methodology. Instead, by avoiding mention of this observation entirely, NASA created an information vacuum that others will fill with speculation, much of it less measured and careful than what the agency's own scientists could provide. This is counterproductive at every level. It damages the institution's credibility, it deprives the public of information they deserve, and it fails to generate the kind of productive scientific dialogue that anomalous observations should spark. So as we continue cataloguing the remaining mysteries surrounding 3I Atlas, remember that each one represents not just a scientific puzzle about this object, but also a failure of scientific communication about how extraordinary our observations of it have truly been. Let's talk about size, because what might seem like a simple question of how big 3I Atlas is actually reveals one of the most statistically shocking aspects of this entire situation. When we detect interstellar objects, when we spot something moving through our solar system on a trajectory that indicates it came from beyond the Sun's gravitational influence, one of the first things we try to determine is its physical dimensions. How large is this visitor? How much mass does it contain? These measurements matter, because they tell us about the object's origin, about the population of interstellar material drifting through the galaxy, about whether what we're detecting is representative of typical objects or unusual outliers. Size determination is challenging when you're observing from tens or hundreds of millions of kilometers away, when all you can measure is brightness, and you have to infer physical dimensions based on assumptions about surface reflectivity and composition. But even with those uncertainties, we can establish rough magnitude estimates, and those estimates for 3I Atlas are stunning. This object is large. Not just large in some abstract sense, but large compared to every other interstellar visitor we've ever detected. Let me give you context for what that means. Oumuamua, the first confirmed interstellar object discovered in 2017, was estimated to be a few hundred meters across at most, possibly smaller depending on its exact shape and reflectivity. It was roughly the size of a tall building, maybe comparable to a large asteroid fragment. 2I, Borisov, the second interstellar object confirmed in 2019, was similarly modest in scale, estimated at perhaps a kilometre or so in diameter, based on cometary brightness and outgassing activity. Both objects were detectable but small, the kinds of things you'd expect to find drifting through space as debris from planetary system formation processes. Objects that size are common as solar system asteroids and comets, so finding similar-sized things in interstellar space makes sense. They represent the chips and fragments that get ejected during planet formation, the material that escapes into the galaxy as individual chunks rather than accreting into larger bodies. 3. Atlas is different. Size estimates based on its brightness, its distance, and its observed activity level suggest it's significantly larger than either of its predecessors. We're potentially talking about something multiple kilometers in diameter, possibly larger depending on surface properties and exact composition. That puts it in a completely different category, not a fragment but a substantial body, something more comparable to the larger comets and asteroids we see within our own solar system. Now, you might think, so what? Space contains objects of all sizes. Why is it surprising that we detected a large one? Here's why. The distribution of object sizes in space follows predictable statistical patterns. Small objects vastly outnumber large ones. This isn't unique to any particular environment. It's a universal pattern that emerges from how material accumulates and fragments over time. Whether you're looking at asteroids, comets, interstellar dust, or debris of any kind, you find the same basic relationship. For every large object, there are many more medium-sized objects, and vastly more small objects. This distribution is usually described mathematically as a power law, where the number of objects increases dramatically as size decreases. The exact exponent varies depending on the specific population you're examining, but the general trend is always the same. Big things are rare, little things are common. This means that when you start detecting objects from a population, when you begin spotting things that were previously too far or too faint to observe, you should find small things first. The first few detections should be the lower end of the size range, simply because those objects are statistically far more numerous. Only as your detection capabilities improve, as you get better telescopes or more sensitive survey programs, should you start finding the larger objects that are rarer, but also somewhat easier to detect individually because of their greater brightness. So here's the problem. We've detected 3 interstellar objects total. Just 3. That's an incredibly small sample. And yet the third one, the most recent one, is by far the largest. By far. It's potentially thousands of times more massive than Oumuamua, It's substantially larger than Borisov. This is the opposite of what statistical expectations predict. Think about what this means in practical terms. If interstellar objects follow the same size distribution patterns we see in other debris populations, then for every object the size of 3I Atlas drifting through the galaxy, there should be hundreds or thousands of smaller objects, things the size of Oumuamua or even smaller. We should have detected dozens or hundreds of those smaller objects before we ever found something as large as 3I Atlas. The fact that we detected a large object as only the third member of our sample suggests something deeply anomalous is happening. Either interstellar space has a very unusual size distribution that somehow concentrates large objects at frequencies way above what natural processes should produce, or our detection methods have biases we don't understand that make us systematically miss the small objects we should be finding. Or 3. I Atlas itself is anomalous, an outlier whose large size reflects something unusual about its origin or nature, rather than representing a random draw from a typical population. Let's think through each possibility. The unusual population distribution hypothesis would require that interstellar space contains far fewer small objects than we expect. Maybe ejection mechanisms that send material out of planetary systems preferentially launch larger objects. Maybe smaller objects get destroyed more readily during their journeys through the harsh, interstellar environment, eroded by radiation or disrupted by collisions with interstellar gas and dust over millions of years of travel. Maybe there's some selection effect we don't understand that removes small objects from the interstellar population. These explanations are possible in principle, but they require overturning well-established understanding of how debris populations form and evolve. They require special pleading, invoking processes for which we have no direct evidence just to explain away the statistical anomaly. That doesn't mean they're wrong, it just means they're unsatisfying without additional supporting evidence. The detection bias hypothesis is more plausible. Maybe our survey telescopes, the automated systems that scan the sky looking for moving objects, have sensitivity limits and search algorithms that make them better at finding large bright objects than small faint ones. Maybe the specific geometries and brightness patterns of smaller interstellar visitors make them harder to distinguish from background noise or from the much more numerous population of ordinary solar system asteroids and comets. Maybe we've missed hundreds of Oumuamua-sized objects simply because they weren't bright enough or didn't move in quite the right way to trigger our detection software. This is testable. As survey technology improves, as we deploy more sensitive instruments and more sophisticated analysis algorithms, we should start finding those smaller objects if they're out there. The fact that current surveys might be biased toward detecting larger objects first would actually be reassuring in a way, because it would mean the population distribution is normal and we're just seeing a skewed sample due to instrumental limitations. But there's a third possibility that's harder to dismiss given all the other anomalies we've been discussing. Maybe 3I Atlas is genuinely unusual. Maybe its large size isn't a random draw from a typical distribution, but rather reflects something specific about this object's history or origin. Maybe it's not representative of typical interstellar debris. Maybe it's something rarer, something formed through processes or circumstances that aren't common in the galaxy. I'm not going to speculate wildly about what those circumstances might be. I'm simply noting that when an object shows multiple anomalous properties simultaneously, when it's unusual in its trajectory and its chemistry and its visible features and its size, you have to consider whether these anomalies are connected, whether they're all pointing toward the same underlying explanation, rather than each being independent coincidences. And here's where NASA's silence becomes even more troubling. The size of 3I Atlas, while uncertain in absolute terms, is clearly unusual compared to previous detections. This comparison doesn't require precise measurements. It doesn't require knowing exact dimensions down to the meter. It simply requires recognizing that this object is substantially larger than the other interstellar visitors we've found, and that this size relationship is statistically unexpected given our tiny sample size. This is the kind of observational fact that should have been highlighted in any honest presentation of what we know about this comet. NASA should have said something like, 3I Atlas appears to be significantly larger than previous interstellar objects, which raises interesting questions about whether our detection methods are biased toward finding larger objects, or whether the size distribution of interstellar material differs from what we expected. That would have been accurate. That would have been informative. That would have invited exactly the kind of scientific discussion that observations like this should generate. Instead, we got nothing. No mention of size comparisons, no discussion of statistical distributions, no acknowledgement that detecting a large object in such a small sample is noteworthy. The press conference treated dimensions as an afterthought, something difficult to measure precisely, so not worth discussing in detail. But the pattern we've established by now makes it clear this wasn't mere oversight. This was consistent with every other aspect of how NASA handled these observations. Emphasize the ordinary, downplay the unusual, avoid anything that might generate questions or complicate the reassuring narrative. And the cumulative effect of this pattern, as we continue adding anomaly after anomaly to our list, is to completely undermine the credibility of that narrative. You can't claim everything looks normal and expected when the object is unusually large, has unusual chemistry, follows an unusual trajectory, displays unusual visible features, and was released through unusual timing mechanisms. At a certain point, the strain between official messaging and observable reality becomes too great to ignore. We're past that point. We've documented 5 distinct anomalies now, 5 separate ways in which 3i Atlas deviates from simple expectations or differs from previous observations. Each one individually might be explained away with sufficient creativity, but collectively, they paint a picture of an object that demands serious investigation rather than bland dismissal. And we still have 3 more anomalies to discuss, 3 additional mysteries that NASA's press conference ignored, 3 further reasons to question whether the institutions charged with exploring our cosmic neighborhood are communicating honestly with the people who fund that exploration. So let's continue, because the next anomaly connects 3i Atlas to one of the most famous unsolved mysteries in the history of radio astronomy, a connection that's either an extraordinary coincidence or a clue to something profound about this object's origin. In August of 1977, a radio telescope at Ohio State University detected something extraordinary. A radio signal, incredibly strong, incredibly narrow in frequency, lasting for exactly the duration that the telescope's beam swept across that region of the sky. The astronomer reviewing the data printout the next day was so struck by the signal's characteristics that he circled it and wrote "wow" in the margin, giving the detection its now famous name. The WOW signal has never been explained. It's never been detected again despite numerous attempts to find a repeat transmission. It came from a region of the sky with no obvious source, no nearby stars that seem like plausible origins. Decades of analysis and speculation have failed to produce a definitive explanation. Natural astronomical phenomena don't typically produce signals with those characteristics. Artificial sources remain a possibility that can't be ruled out, though equally can't be confirmed without additional evidence that has never materialized. The WOW signal sits in astronomical history as a genuine mystery, something we observed but cannot explain, something that might be nothing or might be profoundly important. Now, what does this have to do with 3i Atlas? Here's the connection that makes me pause, that makes me think harder about this interstellar visitor and what investigation strategies we should be pursuing. When you trace back the trajectory of 3i Atlas, when you calculate where it came from before entering our solar system, when you project its path backward through space, that path takes it through a region of the sky that lies very close to where the WOW signal originated. Not exactly the same coordinates, because celestial geometry and measurement uncertainties create some ambiguity, but within roughly 9 degrees of angular separation. In the vast expanse of the entire sky, which spans more than 40,000 square degrees, having these 2 anomalous phenomena separated by decades in time point back to nearly the same region is statistically noteworthy. It's the kind of detail that should make you stop and wonder whether there might be a connection. Now let me be very clear about what I'm not claiming. I am not saying that 3i Atlas is the source of the WOW signal. I am not arguing that this object is transmitting radio waves. I am not suggesting that both phenomena are definitely linked by some causal relationship. What I am saying is that when you have 2 unexplained observations that share a spatial association, when 2 mysteries point to the same region of the cosmos, that coincidence is worth investigating. It might mean nothing. Coincidences happen. With enough data points scattered across the sky, you'll always find some apparent patterns just by chance. But you can't determine whether a coincidence is meaningful or meaningless without actually investigating it. You have to look, you have to gather more data, you have to test whether there's any substance to the apparent connection, or whether it's genuinely just random alignment. That's what science does with interesting correlations. It investigates them. And in this case, investigation means pointing radio telescopes at 3i Atlas and listening. If this object is emitting radio waves, if there's any connection to the WOW signal phenomenon, if there's anything unusual happening at radio frequencies, we should be able to detect it. Radio astronomy is a mature field with incredibly sensitive instruments. We can detect extraordinarily faint signals from enormous distances. If 3i Atlas is transmitting anything stronger than natural background radiation, our telescopes will pick it up. So when I learned about the trajectory coincidence with the WOW signal origin, I did what any curious scientist would do. I contacted radio astronomers who have access to the necessary instruments and asked whether anyone had been monitoring 3i Atlas at radio frequencies. The answer was yes. Observations had been conducted, searches had been performed, and here's what those searches found. Nothing unusual, no strong narrowband signals, no artificial-looking transmissions, no radio signatures that would indicate active broadcasting or unusual electromagnetic activity. Does this mean there's no connection to the WOW signal? Not necessarily. The WOW signal was a one-time event detected at a specific frequency during a specific moment. If there's any relationship to 3i Atlas, it might be that this object passed through that region of space decades ago, and whatever generated the signal then is not generating it now, either because the object's state has changed, or because the emission was genuinely a brief transient event that doesn't repeat. Alternatively, the connection might be indirect. Maybe both phenomena relate to something in that region of the galaxy, some feature or circumstance we don't understand yet that could explain both the 1977 signal and the origin of this interstellar visitor. Or maybe, most likely, there's no connection at all. Maybe the spatial coincidence is exactly that, a coincidence, a random alignment that appears meaningful only because we're looking for patterns, and patterns can emerge from noise. But here's my point. The reason this counts as an anomaly worthy of inclusion in this discussion. The coincidence exists. The spatial association is real, regardless of whether it's causally meaningful, and that association, combined with all the other unusual aspects of 3i Atlas, makes this object worthy of intensive investigation, including at radio frequencies. The fact that initial searches didn't find anything doesn't mean searches shouldn't have been conducted. It doesn't mean the question wasn't worth asking. It simply means that particular hypothesis, the idea that this object is actively transmitting detectable radio signals right now, doesn't appear to be supported by current evidence. That's a useful scientific result. Negative results are still results. They narrow the space of possibilities. They eliminate explanations that don't match observations. They guide future investigation toward more productive avenues. What troubles me is that NASA's press conference didn't mention any of this. They didn't mention the trajectory connection to the WOW signal origin. They didn't mention that radio observations had been conducted. They didn't discuss what those observations did or didn't find. They avoided the entire topic, presumably because raising the WOW signal in any context risks inviting speculation about artificial origins or extraordinary explanations. But avoiding that speculation by simply not mentioning relevant information is intellectual cowardice. It's an insult to the public's intelligence. It's a failure to trust that people can handle complexity and uncertainty. Because here's how this should have been presented. Interestingly, 3i Atlas's trajectory traces back to a region of the sky near where the famous WOW signal was detected in 1977. This spatial coincidence prompted radio astronomers to conduct searches for any unusual radio emissions from the object. Those searches, performed with high sensitivity at multiple frequencies, did not detect significant radio signals beyond normal background levels. While we cannot establish any confirmed connection between the object and the historical signal, the coincidence highlights why this interstellar visitor deserves thorough investigation across multiple wavelengths and using various observational techniques. That statement would have been honest, it would have been informative, it would have acknowledged an interesting correlation without overclaiming its significance. It would have explained what investigation was prompted by that correlation and what results were obtained. It would have treated the audience as capable of understanding nuanced scientific reasoning. Instead, we got silence. And that silence, combined with the pattern of silence surrounding every other anomaly we've discussed, creates exactly the information vacuum that allows speculation to flourish unchecked by factual grounding. When institutions refuse to discuss interesting observations, When they avoid mentioning details that might complicate their preferred narrative, they create space for others to fill that vacuum with theories and explanations that might be far less carefully reasoned than what the institution's own experts could provide. This is self-defeating institutional behavior. NASA presumably stays silent about things like the WOW signal connection because they don't want to encourage wild speculation about alien spacecraft or interstellar communications. But the silence doesn't prevent speculation. It just ensures that speculation happens without NASA's voice in the conversation, without the guidance and context that expert analysis could provide. It ensures that when people do learn about these connections, as they inevitably will because the data is public and researchers are independent, their first question will be not, what does this correlation mean? But rather, why didn't NASA tell us about this? And that second question, that question about institutional transparency and trust, is far more corrosive to public confidence than any reasonable discussion of observational coincidences would have been. So here we have the sixth anomaly, a spatial association between 3I Atlas's origin trajectory and one of astronomy's most famous unsolved mysteries, an association that prompted scientific investigation, that investigation yielding null results but demonstrating appropriate scientific curiosity, and all of it completely absent from official presentation of findings. The pattern is unmistakable now. We're not dealing with oversight or communication failure, we're dealing with deliberate curation of information, systematic avoidance of anything that might generate questions or challenge the carefully constructed message that this object is ordinary and unremarkable. And we still have two more anomalies to examine, two final pieces of evidence that this interstellar visitor behaves in ways we've never seen before, and deserves far more attention than NASA's bland press conference suggested. We've covered trajectory, chemistry, size, spatial coincidences, and visible features. Now let's talk about motion and dynamics, about how 3I Atlas moves through space and how that motion deviates from what pure gravitational mechanics would predict. This brings us to two related anomalies that I'm going to discuss together, because they're connected through the physics of cometary outgassing and how jets of gas affect an object's trajectory. When a comet approaches the Sun and begins to heat up, frozen materials on its surface sublimate, transforming directly from solid into gas. This outgassing doesn't happen uniformly across the entire surface. It happens preferentially from areas where sunlight is most intense, from active vents or fissures where subsurface materials can escape, from regions where the surface composition or structure allows volatile materials to reach space. The result is that gas jets emerge from specific locations on the comet's nucleus, shooting material out into space in particular directions. Now, here's where Newton's laws become relevant. Every action has an equal and opposite reaction. When a comet ejects gas in one direction, the nucleus experiences a thrust in the opposite direction. This thrust is tiny compared to the gravitational forces from the Sun and planets, but it's not negligible. Over weeks and months, these small continuous pushes can measurably alter the comet's trajectory. Astronomers call this non-gravitational acceleration, and it's been observed in many comets over the history of orbital mechanics. It's expected, it's normal. What matters for understanding a specific comet is figuring out the magnitude and direction of these non-gravitational forces, because those details tell you about the outgassing pattern, which in turn tells you about the comet's rotation, its surface properties, where active regions are located, and how it's responding to solar heating. So when we track 3I Atlas's position over time and compare its actual path to what pure gravitational calculations predict, we can measure any deviations and attribute those deviations to outgassing thrust. And here's where things get interesting. The non-gravitational acceleration detected for 3I Atlas doesn't match simple models. In a simple scenario, you'd expect outgassing to be strongest when the comet is closest to the Sun, when heating is most intense, when temperatures drive maximum sublimation. You'd expect the thrust direction to be roughly aligned with the Sun-Comet line, pushing the nucleus in the antisolar direction because that's where most of the gas is escaping. You'd expect the magnitude to correlate with the object's heliocentric distance and its visible brightness, with stronger outgassing producing both more visible coma activity and larger trajectory perturbations. But detailed analysis of 3I Atlas's motion suggests the relationship between outgassing and trajectory perturbation might be more complex than these simple models predict. The timing of acceleration changes, the direction of the applied forces, the magnitude relative to observed brightness variations. Some of these details don't fit perfectly into straightforward cometary behavior. Now, I need to be careful here because orbital mechanics is complicated, and uncertainties in trajectory measurements can create apparent anomalies that aren't real. When you're tracking an object's position from Earth-based telescopes, separated by hundreds of millions of kilometers from the target, tiny measurement errors accumulate. When you're trying to separate gravitational accelerations from non-gravitational ones, you need very precise position data spanning long time periods. The analysis is challenging and subject to revision, as more observations are incorporated. So I'm not claiming that the non-gravitational acceleration of 3I Atlas definitively violates cometary physics or requires extraordinary explanations. What I'm saying is that preliminary analyses suggest complexity that deserves further study, that the dynamics don't appear to be as straightforward as they are for typical comets, and that this complexity is another item on the list of reasons why this object is interesting. Related to this acceleration question is the issue of jet orientations, which brings us back to the forward-facing plume we discussed much earlier, but from a different perspective. When we observe active comets with sufficient resolution, we can often see individual jets, distinct streams of gas and dust erupting from specific locations on the nucleus. These jets have orientations determined by the geometry of the active vents and the rotation state of the nucleus. In typical cases, because outgassing is driven by solar heating, jets tend to point away from the sun. They emerge from the sunlit side of the nucleus and stream outward in directions that have at least some component pointing away from the solar direction. But 3I Atlas appears to show jets or outgassing patterns that don't follow this simple geometry. Some of the brightness features visible in the imaging suggest material is being ejected in directions perpendicular to the sun, or even, as we discussed, in the forward direction along the object's motion. Why would this happen? One possibility is that the nucleus is rotating in such a way that active vents are carried into orientations where their gas jets don't align with the simple sunward-anti-sunward axis. Cometary rotation can be complex with tumbling motions that create time-varying jet directions. If the rotation period and axis orientation produce particular geometric configurations, you might see jets pointing in unexpected directions at certain times. Another possibility is that the outgassing isn't driven purely by solar heating, but has contributions from other energy sources. Maybe the object's interior contains volatile materials that sublimate due to internal heat rather than just surface heating. Maybe there are chemical reactions occurring below the surface that release gases independent of solar input. These would be unusual circumstances, but not impossible, and they could produce jet orientations that don't follow the expected solar-driven pattern. There's also the possibility that what we're interpreting as jet orientations are actually something else entirely, some feature of how dust scatters light, or how the imaging process creates apparent structures that aren't real physical jets. This is why high-resolution imaging matters so much. You need to see fine details clearly to distinguish genuine physical features from observational artifacts. The Mars Reconnaissance Orbiter images, while valuable for being the best we have, still show 3I Atlas as a fairly fuzzy blob, not as a sharply resolved nucleus with distinct jets visible. So there's ambiguity in interpretation. But even granting all these uncertainties, the overall pattern of what's visible and how it compares to theoretical expectations suggests something atypical is happening with this object's outgassing geometry, and that atypical geometry connects directly to the question of non-gravitational acceleration, because the direction and magnitude of thrust depend on where and how gas is being ejected. So these are really two manifestations of the same underlying anomaly. The jets don't orient as expected, and the trajectory perturbations don't behave as simple models predict. Both observations point toward an outgassing pattern that's more complex than typical cometary activity. Both deserve investigation to understand what's happening physically, and both, predictably, were completely absent from NASA's press conference discussion. There was no mention of non-gravitational forces, there was no analysis of jet orientations, there was no discussion of rotation state or outgassing asymmetries. The presentation treated 3I Atlas as if its behavior were entirely ordinary, as if tracking its motion revealed nothing more interesting than standard cometary activity, as if the observations required no deeper analysis beyond confirming the object exists and is roughly where calculations predicted. This brings us to the end of our catalogue of anomalies. We've examined 8 distinct aspects of 3i Atlas that deviate from simple expectations or differ from previous observations. The forward-facing plume visible in imaging, the timing and transparency issues surrounding data release, the ecliptic alignment of its trajectory, the nickel detection without proportional iron, the unusually large size given the small total sample of detected interstellar objects, the spatial association with the WOW signal origin, the complex non-gravitational acceleration pattern, the unusual jet orientations, 8 separate observational features that collectively paint a picture of an object that demands serious investigation rather than bland dismissal. Some of these anomalies might have straightforward explanations once we gather more data. Some might turn out to be less significant than they currently appear, but you can't determine which anomalies are meaningful and which are artifacts without actually investigating them. Without conducting the observations and analysis needed to test competing hypotheses, without taking seriously the possibility that this interstellar visitor might be teaching us something new about comets or about the material drifting through the galaxy. And that possibility, that opportunity to learn something genuinely new, that's what makes NASA's approach to this entire situation so frustrating and disappointing. Instead of excitement about mysteries to solve, we got reassurance that mysteries don't exist. Instead of transparency about unusual observations, we got carefully curated information designed to minimize curiosity. Instead of honest acknowledgement that we don't fully understand this object yet, we got confident proclamations that everything fits expectations. This approach doesn't serve science. It doesn't serve the public. It doesn't serve the goal of building trust in scientific institutions. What it serves is an institutional impulse toward control, toward managing public perception, toward avoiding the discomfort of admitting uncertainty. And while that impulse is understandable from a bureaucratic standpoint, it's completely contrary to everything science is supposed to represent. So now that we've laid out all 8 anomalies, now that we've documented the pattern of avoidance and selective transparency, the question becomes, what should happen next? How should these observations be followed up? What does responsible scientific investigation look like when confronted with an object this unusual? That's what we need to discuss as we move toward conclusion, because December 2025 brings an opportunity, a chance for better observations and better communication, and how that opportunity is handled will tell us whether the pattern we've identified continues or whether NASA recognizes the need for a different approach. So we've spent most of this discussion examining what went wrong, cataloguing the failures of transparency and communication that characterized NASA's handling of 3i Atlas observations. Now let's shift our focus toward what should happen, what responsible scientific investigation and public communication should look like as this interstellar visitor continues its passage through our solar system. Because the story isn't over. The press conference might have been disappointing, but the object itself remains accessible to observation, and we're approaching a crucial window of opportunity that could answer many of the questions we've raised. In December 2025, 3i Atlas will make its closest approach to Earth, passing at a distance that, while still measured in millions of kilometers, represents our best chance for detailed study. This close approach is exactly what every astronomer who cares about interstellar objects has been waiting for, the moment when our most powerful instruments can be brought to bear with maximum effectiveness. And the astronomical community is preparing. Observing time has been allocated on major telescopes around the world. Hubble Space Telescope will be turned toward 3i Atlas to capture images with resolution far superior to what the Mars Reconnaissance Orbiter could achieve. James Webb Space Telescope, with its incredible infrared sensitivity, will observe the object's thermal emission to determine temperature distribution across its surface, to characterize the composition of gases being released, to measure properties that visible light observations cannot reveal. Ground-based observatories, including the largest optical telescopes, will track the object continuously, gathering spectroscopic data across multiple wavelengths, monitoring changes in brightness and activity as solar heating varies with distance, building a comprehensive dataset that will allow detailed modeling of the object's behavior. Radio observatories will continue their searches, listening for any unusual emissions, mapping the object's motion with the extraordinary precision that radar ranging provides when targets are close enough. This is how science should work. This is the appropriate response to encountering something unusual and poorly understood. You observe it as thoroughly as possible. You gather data from multiple sources using different techniques. You compare observations with theoretical predictions. You test competing hypotheses. You follow the evidence wherever it leads, remaining open to surprising conclusions while demanding that conclusions be supported by rigorous analysis rather than speculation. The December observations will be crucial for addressing the anomalies we've discussed. High-resolution imaging will show whether the forward-facing plume is a persistent feature or a transient artifact, whether jets have unusual orientations or whether what appeared unusual in earlier images was a matter of viewing geometry. Spectroscopic observations will provide definitive measurements of elemental abundances confirming or refuting the nickel without iron pattern, identifying other compositional peculiarities if they exist. Precise position measurements will refine our understanding of the object's trajectory and non-gravitational forces, allowing detailed modelling of its rotation and outgassing dynamics. What we learn from these observations will matter. The data will either resolve the mysteries by revealing that anomalies were artifacts of limited earlier observations, or it will deepen the mysteries by confirming that this object truly does behave unlike anything we've encountered before. Either outcome is scientifically valuable. Either outcome advances our understanding, but the outcome will only matter, the public will only benefit from these observations, if the results are communicated honestly and transparently. If NASA and other institutions repeat the pattern we saw in November, if they again present carefully curated subsets of findings while avoiding discussion of anything unusual, if they again prioritize reassurance over inquiry, then the December observations will represent a missed opportunity not just for public engagement, but for scientific progress itself. Because science advances through open dialogue, through multiple researchers independently analysing data and challenging each other's interpretations, through transparency that allows errors to be caught and insights to be shared. You can't have that open dialogue if data is withheld or its significance is downplayed by the institutions controlling access to observational resources. So here's what I'm calling for, what I think everyone who cares about science and space exploration should demand. First, when the December observations are completed and initial analysis has been performed, release the data publicly and promptly. Don't wait months for final peer-reviewed papers. Don't hold back results until every detail has been interpreted and every uncertainty resolved. Release images and spectra and positional measurements into public archives where other researchers can access them, analyse them independently, and contribute their expertise to understanding what they reveal. This is standard practice for most astronomical observations, and there's no reason 3i Atlas should be treated differently. Second, when NASA or other agencies hold briefings or issue press releases about those observations, make sure the presenters are actual scientists who have analysed the data, not public affairs specialists reading prepared statements. Let researchers explain what they found, what they expected to find, where observations match predictions and where they didn't, what questions remain open and what additional work is needed. Trust the public to handle complexity and uncertainty. Trust that excitement about genuine mysteries generates more positive engagement than bland reassurance about normalcy. Third, acknowledge anomalies honestly. If the high-resolution images show features that don't match simple cometry models, say so. If spectroscopic data confirms unusual chemical patterns, discuss them. If trajectory analysis reveals dynamics we don't fully understand yet, admit that uncertainty. Science is strongest when it's honest about what it knows and what it doesn't know. Pretending to have answers when questions remain doesn't strengthen institutional credibility. It damages it. Fourth, engage with the broader scientific community. There are researchers at universities around the world who would love to contribute their expertise to understanding this object. There are specialists in cometry physics, in orbital dynamics, in spectroscopy, in observational techniques, who have insights and analysis methods that could advance our knowledge. Don't treat 3i Atlas as a proprietary discovery to be guarded and controlled. Treat it as a cosmic treasure to be studied collaboratively by everyone with relevant skills and interests. And fifth, recognize that public interest in this object is not a problem to be managed, but an asset to be cultivated. People are curious about interstellar visitors. They want to know what we're learning about objects from beyond our solar system. They're excited by the possibility that observations might reveal something unexpected, something that challenges our assumptions and expands our understanding. That excitement is exactly what space agencies should be nurturing because it translates into public support for space exploration funding, into young people pursuing careers in science and engineering, into a scientifically literate citizenry that understands the value of research and discovery. Treating public curiosity as something dangerous that might lead to wild speculation, if not carefully controlled, that attitude is counterproductive and insulting. The public funds this work. The public deserves to share in the excitement when that work yields interesting results. Looking ahead to December and beyond, we have an opportunity to do this right. We have an opportunity to demonstrate that scientific institutions can communicate honestly about uncertainty while maintaining public trust and enthusiasm. We have an opportunity to show that mysteries are features, not bugs, that the questions we can't yet answer are exactly what make exploration worthwhile. The observations will happen, the telescopes will gather their data. The question is whether the results will be shared openly and discussed honestly, or whether they'll be filtered through the same institutional impulse toward control and reassurance that characterized the November press conference. My hope, my genuine expectation, is that the pattern we've seen will change, that criticism will be heard, that the obvious failures of the earlier approach will be recognized and corrected. But hope isn't certainty, and we'll need to watch carefully to see whether the December brings a different kind of scientific communication or more of the same. What I can tell you is that regardless of how institutions handle this, the scientific community will continue investigating, researchers will continue analysing, and truth will eventually emerge through the process of open inquiry that defines how science actually works, as opposed to how bureaucracies sometimes wish it worked. The anomalies we've discussed are real, the data exists, the questions are genuine, and they will be answered, either through official channels that embrace transparency or through independent research that refuses to be constrained by institutional preferences. That's the beautiful thing about science. It's ultimately self-correcting. It ultimately resists manipulation. It ultimately serves truth rather than narrative. The only question is whether that truth emerges quickly through open collaboration or slowly through the friction of institutional resistance. And that choice lies with the agencies and organizations that control observational resources and communication platforms. Choose well, because the public is watching, and trust once lost is extraordinarily difficult to rebuild. Let's step back from the specific details of 3i Atlas for a moment, and think about something more fundamental, something about the nature of science itself and what mysteries represent in the pursuit of knowledge. There's a tension that exists in how scientific institutions, particularly large government agencies like NASA, approach the unknown. On one hand, scientists are trained to be excited by mystery, to see unanswered questions as opportunities rather than threats, to recognize that the most profound advances in understanding come from observations that don't fit existing models. Every major discovery in the history of astronomy emerged from someone noticing something unexpected and having the courage to take it seriously. The phases of Venus that supported heliocentric cosmology, the anomalous motion of Mercury that required general relativity to explain, the cosmic microwave background that confirmed Big Bang cosmology, the accelerating expansion of the universe driven by dark energy. Every one of these breakthroughs began with an observation that didn't match predictions, with data that challenged prevailing theories, with mysteries that demanded investigation. But institutions, while made up of scientists, don't always behave the way scientists behave. Institutions have different priorities and pressures. They worry about public perception. They worry about funding stability. They worry about political scrutiny. They worry about being associated with fringe ideas or controversial hypotheses that might damage reputation. And those institutional worries create an impulse toward caution, toward presenting findings in ways that emphasize certainty and normalcy, toward avoiding acknowledgement of mysteries that might invite speculation or generate uncomfortable questions. This impulse is understandable. Nobody wants their organization to become associated with wild theories or to be mocked for taking seriously observations that later turn out to be instrumental artifacts or measurement errors. But the protective caution that institutions deploy to guard their reputations ends up working directly against the scientific principles those institutions are supposed to embody. Because here's the thing about mysteries in science. They're not embarrassments. They're not failures. They're not indicators that scientists don't know what they're doing. Mysteries are evidence that we're looking carefully enough to notice when reality doesn't match our expectations, that we're honest enough to acknowledge when observations puzzle us, that we're humble enough to admit the limits of current understanding. When a scientist says, "I don't know," or "this is puzzling," or "we need to investigate further," that's not weakness. That's strength. That's intellectual honesty. That's the foundation of how knowledge actually advances. And when institutions try to hide mysteries, when they downplay anomalies, or avoid discussing observations that don't fit simple explanations, they're not protecting science. They're undermining it. They're suggesting that uncertainty is dangerous, that unanswered questions reflect poorly on researchers, that the public needs to be shielded from the complexity of how discovery actually works. But the public doesn't need that protection. The public isn't stupid. The public isn't so fragile that hearing about scientific mysteries will cause panic or loss of faith in expertise. What actually damages public trust isn't acknowledging uncertainty. It's pretending certainty exists where it doesn't. It's getting caught filtering information or manipulating messages. It's the pattern of behavior we've documented with 3i Atlas, where multiple anomalies go unmentioned in official presentations while being visible to anyone who examines the data independently. That's what creates suspicion. That's what generates conspiracy theories. That's what makes people wonder what else isn't being said, what other information is being held back, whether institutional statements can be trusted at all. And once that trust is damaged, it's extraordinarily difficult to repair, because every future statement gets viewed through a lens of skepticism, every claim gets questioned, every reassurance gets doubted. So here's the better approach, the approach that actually serves both science and public trust. Embrace mystery. Acknowledge it openly. Communicate it honestly. When observations reveal something unexpected, say so. Explain what was expected and why. Explain what was actually observed and how it differs. Discuss possible explanations, including ones that might seem unlikely but can't yet be ruled out. Lay out what additional observations or analysis are needed to distinguish between competing hypotheses. Treat the audience as partners in the investigation, rather than as children who need simplified stories with neat conclusions. This approach doesn't weaken institutional authority. It strengthens it by demonstrating intellectual honesty, by showing that scientists are following evidence rather than defending preconceptions, by inviting the public to share in the excitement of genuine inquiry, rather than being fed predigested conclusions. The history of science is full of examples where acknowledging mystery led to extraordinary advances. When pulsars were first discovered in the 1960s, astronomers genuinely didn't know what they were observing. The regular radio pulses seemed so artificial that the possibility of extraterrestrial signals was seriously considered and openly discussed. Rather than hiding this uncertainty or downplaying the observations, scientists communicated honestly about the puzzle, while conducting additional observations to test different explanations. Eventually, the explanation involving rapidly rotating neutron stars emerged and was confirmed, and pulsars became one of the most important tools in modern astrophysics. But imagine if the initial discovery had been handled differently, if institutions had refused to acknowledge the mystery, had insisted the signals were obviously natural phenomena requiring no special investigation, had avoided discussing the possibility of artificial origin because that might invite speculation. We would have learned less. The investigation would have been less thorough. Public engagement would have been diminished. The eventual explanation would have been less satisfying, because the journey to reach it would have been obscured. That's the model NASA should follow with 3i Atlas. This is an object that exhibits multiple unusual properties. Some might have natural explanations we'll discover through further observation. Some might reflect misinterpretation of limited data that will be corrected when better measurements are obtained. Some might represent genuinely new phenomena that will expand our understanding of how interstellar material behaves, or how comets work, or what populations exist in the galaxy. We don't know yet which category each anomaly falls into. That uncertainty is appropriate. That uncertainty is honest. And that uncertainty is exciting, because it means we have opportunities to learn, opportunities to discover, opportunities to advance knowledge through careful investigation and rigorous analysis. The worst possible response is to pretend the uncertainties don't exist, to present a facade of complete understanding that doesn't match reality, to communicate in ways that discourage rather than encourage deeper inquiry. So as we think about 3i Atlas and how it's been presented to the public, we need to recognize that this isn't just about one interstellar object. This is about the broader question of how scientific institutions communicate about discovery, about mystery, about the inevitable gaps between what we observe and what we understand. And the answer to that question has implications far beyond this particular case. It affects how future discoveries are shared. It affects public trust in science. It affects whether young people see research as an exciting adventure into the unknown, or as a bureaucratic process of confirming what experts already claim to know. It affects whether space exploration maintains public support, or becomes seen as a waste of resources managed by institutions that don't respect the people funding their work. These stakes are high, the choices matter, and what we've seen with NASA's handling of 3i Atlas suggests that institutions still have work to do in learning how to communicate honestly about uncertainty while maintaining credibility and trust. That's a challenge worth taking seriously, because getting it right benefits everyone while getting it wrong damages the entire scientific enterprise. We've covered a lot of ground together, worked through 8 distinct anomalies that make 3i Atlas far more interesting than NASA's November press conference suggested. Let me briefly summarize what we've examined, so you have the complete picture fresh in your mind. First, the forward-facing plume visible in Mars Reconnaissance Orbiter images, a brightness pattern extending ahead of the object's motion, rather than trailing behind as simple cometary physics would predict. Second, the timing and transparency issues surrounding how those images were withheld while other Mars observations continued being released, suggesting selective control of information rather than simple bureaucratic delays. Third, the ecliptic alignment of the object's trajectory, a geometric feature that statistically shouldn't occur with high probability, but did in only our third confirmed interstellar detection. Fourth, the spectroscopic detection of nickel without proportional iron, a chemical signature unprecedented in cometary observations, and inconsistent with how these elements form together in stellar nucleosynthesis. Fifth, the unusually large size of this object compared to the other 2 interstellar visitors we've detected, a pattern that defies the statistical expectation that small objects should vastly outnumber large ones in any detection sequence. Sixth, the spatial association between the object's origin trajectory and the direction of the famous WOW signal, a coincidence that may mean nothing but the prompted legitimate scientific investigation through radio observations. Seventh, the complex non-gravitational acceleration pattern suggesting outgassing dynamics more complicated than simple cometary models predict. And eighth, the unusual jet orientations that don't align with expected solar-driven sublimation geometry. 8 separate observational features, 8 mysteries that deserve investigation, 8 topics that should have been highlighted in any honest presentation of what we know about this interstellar visitor, and 8 silences in NASA's official briefing, 8 deliberate omissions that paint a clear pattern of institutional preference for managing public perception rather than sharing scientific discovery. Now, what does all this mean? What should we take away from this examination of 3i Atlas and how it's been communicated? First, and most important, it means the public-funded science depends on public trust, and that trust requires transparency. When agencies like NASA choose to present carefully curated subsets of information, while avoiding discussion of anything that might complicate their preferred narrative, they're making a choice that ultimately damages their own credibility and undermines public confidence in scientific institutions. Second, it means that mysteries are not threats to be managed but opportunities to be embraced. The anomalies we've discussed don't automatically imply anything extraordinary is happening. They simply mean we don't fully understand this object yet, that observations have revealed complexities requiring further investigation, that the story is still unfolding rather than being complete. That uncertainty is appropriate and healthy. Science isn't about claiming to have all answers. It's about asking better questions and pursuing them honestly wherever they lead. Third, it means that December 2025 brings a crucial test of whether institutions have learned from the failures of the November press conference. The upcoming close approach of 3i Atlas offers the best observational opportunity we'll have, potentially for decades, to study an interstellar object in detail. How those observations are conducted, analysed and communicated will tell us whether the pattern we've documented continues, or whether NASA recognises the need for a different approach. And fourth, it means that all of us who care about space exploration and scientific discovery have a responsibility to demand better. We fund this work through our taxes. We support these missions through our enthusiasm and engagement. We deserve transparency in return. We deserve to hear about the real mysteries our instruments reveal, not just sanitized summaries designed to avoid generating questions. So let me tell you what you can do, what actions you can take to make your voice heard, and to demand the kind of scientific communication that serves public interest rather than institutional comfort. First, stay informed. Follow the December observations. Look for updates from multiple sources, not just official NASA channels. Independent researchers, university astronomers, science journalists covering space topics. These voices will provide perspectives and analysis that institutional statements might omit. Second, engage critically with official communications. When NASA or other agencies issue press releases or hold briefings about 3i Atlas, pay attention to what they emphasize and what they avoid. Ask questions about anomalies that aren't mentioned. Demand substantive answers rather than reassuring platitudes. Make it clear through comments, through social media engagement, through direct communication with representatives, that you expect and deserve transparency. Third, support independent scientific investigation. Researchers working outside large institutional frameworks often have more freedom to pursue unusual observations and discuss anomalous findings openly. When you see scientists taking these mysteries seriously, when you see analysis that acknowledges uncertainties rather than hiding them, amplify that work, share it, discuss it, show that there's public appetite for honest engagement with complexity. Fourth, maintain scientific literacy and critical thinking. Don't swing to the opposite extreme of assuming every mystery implies extraordinary explanations. The goal isn't to replace institutional overcaution with public overinterpretation. The goal is to create space for genuine inquiry, for following evidence carefully and rigorously, for distinguishing between what we know, what we suspect, and what we're still working to understand. And fifth, remember that this is about more than one interstellar comet. This is about the kind of relationship we want between scientific institutions and the public they serve, about whether discovery is shared openly or managed carefully, about whether mysteries are treated as exciting opportunities or as embarrassing secrets. If these 8 anomalies concern you, if you believe the public deserves to know when observations reveal unexpected patterns, if you think that transparency and honesty matter more than carefully controlled messaging, then let your voice be heard. Share this information with others. Talk about what NASA avoided discussing. Demand better from institutions claiming to represent scientific exploration. Because what we've examined here isn't conspiracy theory. This isn't wild speculation disconnected from evidence. Every single anomaly I've presented comes from publicly available data, from peer-reviewed observations, from measurements that anyone with sufficient expertise can verify independently. The information exists. The mysteries are real. The only question is whether the agencies we fund will communicate about them honestly, or whether they'll continue the pattern of selective transparency that characterized the November press conference. In the coming weeks and months, pay attention. Watch how the December observations are handled. Notice whether results are released promptly or delayed. Notice whether presentations include actual scientists or just public affairs specialists. Notice whether anomalies are discussed or ignored. Notice whether the institutional response reflects genuine commitment to transparency or merely performs it while continuing to control and filter information. Your attention matters, your engagement matters, your willingness to demand better communication will influence how institutions behave, because they respond to public pressure even when they resist it initially, and ultimately, this vigilance serves everyone's interest. Science progresses faster when data is shared openly. Public trust is stronger when institutions communicate honestly. Young people are more inspired to pursue scientific careers when they see research as genuine exploration rather than bureaucratic box-checking. Space exploration maintains funding support when taxpayers feel connected to and informed about discoveries made with their resources. So stay curious, stay engaged, stay critical in the best sense of that word, willing to examine claims carefully and demand evidence and transparency. Because what NASA's photos of 3i Atlas don't reveal might indeed be more important than what they show. The hidden mysteries, the unacknowledged anomalies, the pattern of institutional avoidance. These tell a story about how scientific institutions currently relate to the public, and that story needs to change. We deserve better. Science deserves better, and the extraordinary objects visiting our solar system from the depths of interstellar space deserve to be studied and communicated about with the honesty, excitement, and transparency that genuine discovery demands. December approaches. The telescopes are ready. The question is whether the institutions controlling those telescopes are ready to embrace the mysteries they'll reveal and share them honestly with the world. Let's watch together and see.